forward from here. So if we recall, we were looking at the state space representation, and in the previous class, we essentially considered, the solution of the state space equation. And before we went to the solution of state space equation, we considered the first order homogeneous ODE, and then we saw that the solution will be e power at x0, which is this, and e power at is what is called as a state transition matrix, right? And we ended our discussion with a query, that is, if we essentially want to calculate the exponential of a matrix, right? What happens, right? So how do I do that? So if the matrix is, let's say, 1, 2, 0, 1, right? The exponential just by taking, like the exponents of the individual terms and doing it. That's not the case, right? In general. So how do we do that, right? So for that, we use this formula which we have already derived, right? So e power at for any general, state matrix A is obtained, can be calculated as Laplace inverse of Si minus A inverse. Okay, so that is the equation that you and I need to use. So if we want to do it for that example, right, that we consider, that is A was, 1, 2, 0, and 1. What we do is that you and I can essentially form Si minus A and then carry on with it, right? So essentially Si minus A will now become S minus 1 minus 2, 0, and S minus 1. And when we calculate the inverse, it's, as we know, the inverse of a matrix is adjoint by determinant, right? The determinant in this case is, it's a 2 by 2 matrix, right? So we multiply the diagonal terms, which will give me S minus 1 whole square. And then we multiply the off diagonal terms, which will give me 0. So we'll just get S minus 1 whole square. Okay, so that's what we have as the determinant, and that comes in the denominator. How do we get the adjoint of a 2 by 2 matrix? So in this case, the adjoint is we swap the diagonal terms. They still remain as S minus 1 because this is a very special case, special example, right? They remain the same. And what we do is that we swap the off diagonal terms, but then we multiply them by minus 1. So they become 2 and 0 like this. And then we need to take the transpose of it. Okay, so that's how we calculate the adjoint. So the adjoint of this 2 by 2 matrix happens to be S minus 1, 2, 0, and S minus 1. Okay. Now we substitute for that, and then we simplify it, and then we take the Laplace inverse. Then for the Laplace inverse of this 2 by 2 matrix with the functions of S, right? You and I can take the Laplace inverse of the individual factors. The Laplace inverse and Laplace operator, we are allowed to do that. Okay, so that's how the the function is structured. Okay, then what happens is that when we have the Laplace inverse being taken, we have to take the Laplace inverse of the individual terms. And what happens is that the Laplace inverse of S minus 1 becomes e power t. The Laplace inverse, of course, once again, of 1 by S minus 1 becomes e power t. The Laplace of 2 by S minus 1 whole square becomes 2t e power t. Okay. So how do we get that? So we use the properties of Laplace transform. Okay. So which we may have studied in vehicle dynamics, right? So if you recall, when we did Laplace transforms and looked at the properties, let's say we take f of t to be e power t, and the corresponding Laplace transform is 1 by S minus 1. This is a property of Laplace transform. That is, Laplace of t is minus df ds. Okay, that is a property of the Laplace transform. Okay, so if we do minus d by ds of 1 by S minus 1, if we differentiate it, we get 1 by S minus 1 whole square. So consequently, what do we know? The Laplace inverse of 1 by S minus 1 whole square is t times e power t. Okay, so that's what we can find. And we had this factor 2 here, right? That's why the factor 2 remains as it is. So the off diagonal term becomes 2t e power t. and Laplace inverse of 0 is 0 itself, right? So we can immediately observe that the exponential of this matrix, right? The exponential of 1, 2, 0, 1 times t, right, is e power t, 2t e power t, 0 and e power t. Okay, so we can immediately see that it is not the matrix formed by taking the exponentials of the individual elements. Okay, it's something else. That is something which is very important, okay, for you and me to understand. Now, so with this understanding, what we do is that, like, we also take another example where we take A to be a diagonal matrix. So what is a diagonal matrix? A diagonal matrix is one where what it has only non-zero diagonal terms, right? The off diagonal terms are 0. So here we can see that only the diagonal terms, this is the diagonal of the matrix, right? Has non-zero terms. The off diagonal terms are all 0. Okay, so that's the diagonal matrix. So it so turns out that if we repeat the process for a diagonal matrix, the Laplace of a diagonal matrix we get by just taking the Laplace of the not the Laplace, the exponential of a diagonal matrix e power at. You and I need to form the matrix where the diagonal elements will be the exponentials of the individual entries. So what do I mean? Only with a diagonal matrix, if I do this, we don't take Laplace of individual elements. We just put 0, 0 off diagonal. But then the diagonal terms, you and I can write e power t and e power 2t. Okay, but this is a special case. Okay, not always true. Okay, so that should be understood. All right, so I hope this is clear, right? So I hope it's clear how we get the exponential of a matrix, and also like what happens in the case of a diagonal matrix. Okay, so this is how we calculate the state transition matrix. Of course, I'm sharing this for your information. You know, like in our course, by and large, when we do computations by hand, I'm not going to expect you to compute the state transition matrix unless otherwise I give you a problem like this. Okay, but then we should know how to calculate it. And in fact, so are there people who are interested in mathematics for the sake of mathematics in this class? How many of you are interested in mathematics?
Sir, I am interested, sir.
Sir, all are interested, sir. Here.
All are interested. Okay, very good. Okay, so then this is an optional thing. You please search in Google, okay, and then read this paper. Okay, so this is connected to our course because many of the algorithms have been now coded and used in solving ODEs and so on. Okay, which also find application in automotive control because we essentially use the state space representation, right? So two authors, Waller and Van Loon, wrote a paper long ago. Of course, please interpret the word dubious in a light vein. Okay, so they are all correct ways to compute the exponentials of the matrix. They propose not one or two, 19 different methods. Okay, and what you and I have learned is only one method of them. Okay, so I hope it's clear, right? So they propose 19, but then like we learned one method. What was that method? We essentially learned that Laplace e power at is Laplace inverse of Si minus A inverse. Okay, so that's all we need. All right. Okay, fine. Okay, so I hope it is clear how to calculate e power at. Now let's go back to the state equation. So the state equation for you and me is x dot equals ax plus bu. Okay. If we process this, I'm leaving the what to say mathematics steps in between, which you would have learned in the videos, but primarily we take the Laplace transform and process it. If we process that, the important thing is this, right? We get the solution to the state equation to be e power at x0 plus integral 0 to t e power a t minus tau bu tau d tau. Okay, so a little bit complex at first glance, but let's interpret the physics, then things will become easy to understand, right? So if you recall, when we even studied vehicle dynamics, I talked about free response and forced response, right? So what was free response? What was forced response?
Sir, when the forcing free response is when the system is perturbed and lived, like there is no forcing function coming on that.
Okay.
And force responses are basically when it is under some periodic forces or application of force in that way. Then how a system is behaving.
Okay. So essentially, if we look at free response, you need to essentially remember that the free response of the system, right, is due to the initial condition of the system, right? That's why you can see that x0 comes into play, right? So the forced response is due to the input that we get. All right. So that's the best way to understand. Okay. So Roshan, of course, you also told pretty much the same thing, but I'm just clarifying. Okay. So the free response is due to the non-zero initial condition. Let's say we take a pendulum, we tap it, right? So you and I are giving a non-zero initial state, and the pendulum oscillates. Okay. So that is free response. On the other hand, for a forced response, we have the input, right, coming into play, and the input is provided, and the system responds to it. Okay, so that is a forced response. So if you look at this particular expression for the state vector, we can observe two terms. Okay, the first term on the right, which is e power at x0, which is the free response. The second term on the right, which is a integral with exponential functions and so on. But importantly for you and me, it has the input u, right? So that is the system response due to the input that you and I provide. Okay, so that is what is called as a forced response. So by using the output equation, if we calculate y of t, the first term once again, c dot e power at x0 is the free response. Whatever is having the input, that is the forced response. Okay, so we can immediately observe that even the state equation, when it's solved, we are able to get the free response and the forced response. If you recall, even when we did the transfer function based approach, we would have got one what to say, bunch of equations which would have had y0, y dot 0, and so on, right? And then plus one term which would have involved u of x. We would have considered zero initial conditions and taken this as the transfer function. Okay, but then even in the Laplace transform based methods, you and I can analyze free response and forced response. Okay, so so essentially, I think you know these are two equivalent ways of doing the same thing. Okay, so essentially, the state space representation, right? When we solve the state equation, we are going to get these two terms, and that is true even with MIMO systems. Okay, so I've just shared it here. All right. Okay. So, so I hope it is clear how when we take the state equation, we are able to get the free response and the forced response. Okay, so that becomes important for us as we proceed in our analysis, because using the state space representation, we can solve for both the system output due to initial condition and the system output due to the input that we provide. Okay, so both the things can be done. All right. Okay. So now I'm going to do an important example. Okay, so which essentially conveys one interesting thing about the state space representation, and helps us figure things out. Okay, as far as the state space representation is concerned. So what is that? So let's say we consider this example. Okay, where we consider the second order system whose governing equation is y double dot t plus ay dot t plus by equals u dot plus cut. Now, if we take the Laplace transform, apply zero initial conditions, u and I will get this as the transfer function. Okay, so we'll get s plus c divided by a squared plus as plus b. Okay, this I leave it as an exercise. Okay, I'm sure all of you can do this. Okay, so you take Laplace transform on both sides. You take all initial conditions to be 0, and then you cross multiply, and then like you will get the ratio of y of s to u of s to be this. All right. Now, how do we take the state space representation? Okay. So if you recollect how we do the state space representation, sorry. So when we even like did the example of mass spring damper system, right? We took the output displacement y and the speed y dot as two states. Let's try out the same approach even here. Okay, so what happens? So we choose x1 to be y, x2 to be y dot. Now, if we take x1 dot, we get y dot, which is x2. We know this. If we take x2 dot, we get y double dot. And how do I get y double dot? From this equation. So y double dot t is going to be equal to minus byt minus ay dot t plus u dot t plus cut. Okay, so essentially what I have done is that like I have just rearranged the terms in that equation. Okay, and as we know, y of t is x1, right? Y dot of t is x2, and u dot and cut remain. Okay, now what is the next step in the what to say state space representation? We have these two first order ODEs. What we do is that like we essentially collate them into the state equation as a vector first order ODE. Okay, so that is this step. So we write x1 dot x2 dot as a column vector, and we collate these terms. When we collate these terms, we get 0, 1, minus b minus a, x1, x2. Okay, this is obvious, right? Why? Because 0, 1 corresponds to this x2 term, minus b minus a correspond to this term for x2 dot. Okay, so that's clear. Now comes the interesting part. We are left with u dot and u. So we can write it as 0, 1 u dot plus 0 c u. Okay, so we can immediately observe that we have this representation, right? When we write it in the state space form. Okay, but now there is an issue, right? So what is the standard state space representation? It is x dot equals ax plus bu, right? Do we see u dot here? No, right? Then what happens, right? How do I resolve this, right? And essentially take action. That's where things become interesting. Okay, so one may say, hey, look, can I not write u dot and u as some vector and then like take it as a new input? Unfortunately, you and I cannot do such things. Okay, so this is not the state space representation. Okay, this is not a viable state space representation. Why? Because if we end up choosing the state variables as just y and y dot, on the right hand side, in addition to that bu term, we also get some term involving u dot, okay, which is not viable. Okay, then the point is, what do we do, right? How do we resolve this? So the way we do it is by redefining the state variables. We redefine state variables. So when a particular choice of state variables is not able to give us this representation, right? X dot equals ax plus bu. What we need to do is that like we need to try for a new choice. Okay, that's all we need to do, right? So how do we do that? Okay, so then one may ask the question, hey, are we not doing trial and error? Yes and no. Okay, so we are slowly getting to that answer, but I want to drive home the point through this example. So let's now try out, right? One more choice of state variables. So what we do is that like we choose the state variable x1 as y, and we choose the state variable x2 as y dot minus u. of course, one may ask the question, hey, how did you choose this? How did you make, like x2 to be y dot minus u? How did we know? Okay. That's where we will learn what are called canonical forms for state space representation. But let's try it out. Okay. So see, state variables need not have any physical meaning also. Okay. That's one more powerful advantage of the state space representation. Okay. We can, yes, please.
Just to understand something based on this point that you're mentioning, this x2 of t, y dot of t minus u of t, just to physically realize what the equation says is the rate of change of the output is getting subtracted with the input u of t, correct? That
Exactly.
variable we are trying to analyze at each state.
So what I also want to convey as a connected point frame is that the important point is that state variables need not necessarily have a physical meaning. Okay. So one may say, hey, look, if you look at this equation, y dot minus u, let's say y is displacement for the sake of understanding, right? What will be y dot? Velocity, right? Speed, right? So then let's say we give force as an input. U of t will be a force.
Correct.
So now,
exactly my doubt.
Are we subtracting force from speed? Okay, we should not look like that. Look at it like that. Okay, because a unique aspect about state space representation is that it allows us to do all these, I would say, transformations, right? Wherein our state variables need not necessarily have a physical meaning. I hope that's clear. Okay.
Thank you, sir. I did. Yeah.
Okay. So now let's try it out. Okay. Then we will figure out as we go along. How do I pull it out? Right, out of thin air. See, one immediate question which will come to a learner is that, hey, how did we know x2 should be y dot minus u? Why not y dot minus u dot? Right. Natural question to ask. Right. We are coming there. Okay. So we will be learning what are called canonical forms. As we go along, a few canonical forms, right, which are useful in automotive control. Okay. So, but I just wanted to motivate the issue and also motivate motivate one advantage of the state space representation, because in the state space, you can have an infinite number of state space representations for the same system. Okay. We are going to learn that in the next class. Okay. How, but let's proceed with this example first, right?
So what's the purpose of redefining the state space variables?
Redefining the state variables is that, like, many times what will happen is that your computations can become simpler. Okay, we will realize it. Okay, even when we do control design, if we are going to learn something called as a controller canonical form. Okay, when you write the state space representation in the controller canonical form, the calculation of the controller parameters becomes simpler. Okay? So can you still calculate the controller parameters in another state space representation? Of course you can, right? Ultimately you will get the same physical answer. But you and I want to sort of also keep in track the computation, right? Okay? Because state space representation is extremely tied up. So is the transfer function representation, but state space representation is inherently linked to numerical computations that you and I need to do on a microprocessor, right? So then, we want to optimize, right, the numerical operations that we do, right? That's why we choose the appropriate state spaces. I hope it's clear, right?
Yeah, fine, sir. Yes, sir.
So, of course, please remember, you remember the broad historical overview I also provided, right? When did we go from classical control to modern control?
Frequency domain to time domain.
When we did the
When?
1960.
Around 1950s, 1960s. You remember in the very first introduction classes I told you, right? And what motivated that transition?
Power of computation, sir.
Exactly, because so the integrated circuit was invented, right? And digital computers came into being, right? And we could do computations on a digital computer. That's when ODEs have been there for a long time. See, state space representation is nothing new, right? Because as you can see, philosophically, it's just representing an ODE, nth order ODE as n first order ODEs, right? Nothing more than that, right? Just that, we were not ready to have a computational tools before 1950s, 1960s, or till 1940s. When the computational effort came, it naturally picked up. Okay, so that is the point. Okay, so with that background, when we want to rely on a lot of numerical computation, obviously you and I want to do the least possible computation, right? That's why we go for multiple state space representations. Okay, I hope the sort of like a big picture rationale is clear. All right. So let's continue, right, with this particular example. With this choice, x1 dot becomes equal to y dot. But what is y dot now? Y dot is now x2 plus u. Okay, so it's no longer x2, but it's x2 plus u. Okay, so we write that x2 dot is y double dot minus u dot. And what is that? If we go back here, so what is y double dot minus u dot? It is ay dot minus ay dot, sorry. Then sorry,
minus by
minus by
plus cu.
right? Now we substitute, right? This is x2 dot. Okay, what is ay dot? Y dot is x2 plus u, right? So we substitute x2 plus u here. And then what is y? Y is x1, right? And then cu remains the same. So what do you and I get? We get minus bx1 minus ax2 plus what do we have? C minus a times u. Am I correct? We'll have two terms with the input, right? Is it not? Okay. So that's what we have. Minus bx1 minus ax2 plus c minus a, right? So now when we collate these two equations, we get 0, 1 times x1, x2, which is this term, x2, plus 1 times u. Now you can see a difference coming in because even in x1 dot, you have the input u coming in. Then for x2 dot, we have minus bx1 minus ax2 plus c minus, okay, right? And then y of t is nothing but x1, which is 1 dot x1, x2. Okay, so that equation is simple. Now, what do we observe with this state space representation? It is of the form x dot equals ax plus bu. I hope everyone agrees. There is no u dot term here, right? So magically the u dot term has disappeared. Why? Because of the choice of the state variables that you and I made. I hope this point is clear, right? So that is when we started off with this example, you and I chose the first cut state variables that we typically start off with. X1 equals y, x2 equals y dot, right? And we saw that that didn't quite work out. Why? Because we had a u dot term, right, coming into our play, right? And when we have the redefinition of the state variables in this manner, what happens is that we could fit the governing equations into the standard state space representation, right? Which is x dot equals ax plus bu, right? The u dot term vanished. The u dot term didn't vanish. Okay, the u dot term is still there in the governing equation. But where was the u dot term incorporated now? In the evolution of the state variable itself, x2, right? Because you can see that in x2 dot, the u dot term came, and that sort of brought us the standard form. Okay, so I hope this example is clear, right? What we did, how we chose the state variables, we will learn, right? But having chosen x1, x2 in this manner, I hope the algebra is clear, right? Does anyone have any questions with the algebra having chosen x1, x2?
No, sir.
Any
Clear.
questions? Clear. Now comes, hey, how do you choose x1, x2 in the first place? Okay. That's where we will be learning a few canonical state space representations. So what do we mean canonical? Is exactly this, right? That is, you and I will end up learning some state space representations which are standard and useful, so that we can directly choose the state variables from the governing equations and use them for either control design or estimator design and so on. Okay, so all those things we will learn as we go along, and that is where we use this important concept. Okay, so let us say we consider the mass spring damper system, right? Which was mx double dot plus, of course, I'm suppressing time. Yeah, kx equals f. What was the transfer function for the mass spring damper system?
So it is omega n square divided by s square plus 2 j omega n plus omega n square.
That is a standard form, correct, Roshan. But for the mass spin damper system, you remember the Planck transfer function was 1 by ms squared plus cs plus k, right? By taking Laplace transform and applying zero initial conditions, right? I hope all of us remember this, right? Yeah.
Yes, sir.
Yeah. So what I mean to say is that, like, let's say there are 20 of us in this class, right? All of us are given this mass spring damper system with this equation. All of us will get the same transfer function. Okay, no change. However, each one of us can write our own state space representation. All right. So I will show you how in the next class using some matrix algebra. But then, like, we are engineers, right? We also want to apply it to automotive control. Okay, so we learn one useful canonical form, which will help us, right, and which will essentially help us, use this aspect, right, with respect to choosing the state variables and forming the appropriate state space representation, so that, like, we can use it in practice. All right. Okay. So that's something we will be learning as we go forward. Okay. So any questions? Do things seem a little bit fuzzy and like unfamiliar today? No.
Yes, sir. Of course.
And I think that's a good sign, right? Because that's a good sign that the content is new, right? We need to learn.
Yes, sir.
Yes, sir.
Correct. So see, if everything seems familiar, I'm not doing my duty, right? So it should look different and new, right? And puzzling. Then only we learn. But don't worry, as we go along, by in another month's time, when we complete the course, like, this thing will be clear to you, right? Clear to all of us. And as I told you, you will also understand things better when you do a project. Like, we will use the state space representation in the second project, right, on steering control, so that, like, you and I will be able to understand how these concepts are, right? Okay. So, any questions on today's material?
Sir, can we ask some questions based on yesterday's interaction with Abhinav?
Yeah, so you can ask me, but I will defer to him, because see, I don't want to use my guess, right, to say answers without having been present in that meeting, right?
Sure,
But you
sure.
certainly ask. So I think, Prem, you need to take my response with the pinch of salt, right? That is
No problem, sir.
you.
The conceptual aspect of it.
Yeah. Please go ahead. Yeah.
Oh, 1 second. So,
Professor, just Prem, just one question I want to ask. Then you continue with that. Professor, basically in the what I mean to say, vehicle dynamics class also. Okay. Hello. Am I
Yes,
audible, sir?
Roshan, please go ahead.
So basically, sir, you had given us some problems in which I remember very clearly that while solving that, we could face the issue like this only, that UT was coming in the state space. What I mean to say is not in a standard form. And then we had to choose a state variable in such a way that UT becomes a part of the state space equation in such a way that it becomes a standard one. So
Okay.
at that time, probably, just let me share my screen for a minute, sir.
Okay.
I'll just show
Then
again.
then let me stop sharing.
Yeah.
Yeah, please go ahead.
Yes, sir. Just a minute, sir. I think it's visible to you, sir, if I'm
Yeah,
not
yeah,
wrong.
yeah, yeah. Yes,
So
yes, yes.
I found one what I mean to say is state space representation of a scalar differential equation in Ogata, the book of Ogata,
Mm.
and this was like explaining how we should take the state space variable in such a way that even if we have a u function, uh, uh, so that if we select the problem like equation like this, what I mean to say, x is equal to y minus b beta
Exactly.
dot beta u and like this. So by using this exact what I mean to say is standard method,
Mm.
we can definitely get u in absorbed u
Uh,
in the state space variable itself. So is that the thing that
Absolutely.
we are going to learn tomorrow?
Yeah, no, not tomorrow, Roshan. Like in fact, this shows that your batch is way ahead of me, right? So
Oh
I
no,
think I
sir,
should
not at all, sir.
force.
It's basically, sir, it's your blessing that that has triggered our
So,
mind to go and
uh,
explore. That's
uh,
nothing else.
so I'm very happy that you have already figured this one out. So if I can paraphrase what you have told, right? So what you are telling is that, like, you remember we consider that standard equation, right? A naught dny dt n plus a1 dn minus 1 dy dt n minus 1 and so on, right? On the right
Right,
hand side, we had b naught dmu dtm and so on, right? So you remember, Roshan,
right,
for the standard
right, sir,
ODE
right.
for
Very, very clearly.
take or and then we took that transfer function and then like we got a numerator polynomial and a denominator polynomial of orders m and n respectively, right?
Right,
So
sir,
here
right, sir.
also, the starting equation which you are projecting is the same equation with the only
Exactly.
simplification being that m is equal to n. Okay,
Right.
please stay there. Please stay there. Yeah, yeah. So yeah, 2.33, right? Yeah. What you are projecting is that it's the same equation. They are defining derivatives using a superscript. That's all they are doing, right? So, so essentially, they have implicitly assumed m to be equal to n here. Okay, point number one. And they have, if you scroll down, please, come down to the state space. Finally, to the matrix form. Yeah, please stay here, right? So this, comes out in as two common controller canonical forms. This typically is a variant of what we call as an observer canonical form. Okay. So we are also going to learn what is called as a controller canonical form. Okay. So we are not going to go to observer canonical form in this course, but then we are going to learn controller. Okay. So we are going to learn a few canonical forms, which will be helpful to you and me for automotive control design. All right.
Okay, sir.
All right. But I
Thank
think
you,
this shows that I should have tightened up the course a little bit more, right? So I was just keeping it very practical, but I'm very happy that your batch is looking at all the fundamental theory also, right?
sir. It was just because I was not able to solve the problem, so I just took the help of this, nothing else.
Yeah. So we will be learning these, Roshan, okay? But I will not be deriving it to such an extent because, as I told, quote unquote, I'm using an engineer's approach, right? I am going to
Right.
use the results, but not derive them, okay?
Okay,
Derivation, yes. You have already located Ogata, and this is that modern control engineering, right, by Ogata, right?
right, sir. Right, sir. Right, sir.
So one can learn deeper into this because if it were a course on control theory, I would have taught you all these things. But our course is control of automotive systems, where we will learn the relevant concepts, but we will apply it to automotive case studies. And I am also teaching the concepts from an application perspective. Okay? That is the context. Okay. Yeah.
So thank you so much, sir. Thank you so
All
much.
right.
I'll stop
Sir,
sharing,
am I
sir.
audible?
Just,
Am I audible?
Yes, please.
Sir, the question is on that project that Abhinav was given. So,
Please.
what we have context as
Can you? No, I think Prem, can you repeat? Question was on yesterday's project. Yeah, can you then go for it?
So the question is on the first project that we have been given, which is on the brake control. So essentially, what we have been given as a data is the frequency response data file and as well as a step response data file, which is nothing but has the time each time step and following voltage and the pressure signal values. Such a data is given. The requirement is that we'll have to find the step response, frequency response, and then plot a Bode diagram. So when we do that, what exactly is happening is that we are using FFT and we are computing a single-sided amplitude spectrum plot. So I just wanted to know what is happening here.
So I think Abhinav discussed this with me today morning. I explained it to him. He will also explain it to you in the contact session. So what happens is that, like, Prem, there are two things here, right? From the frequency response data, when you do the FFT, you will see that for every frequency, input frequency, I think we would have given from what, 0.1 hertz to 1 hertz. Am I correct?
Yes, sir. 0.1 to 1.2, I believe.
Yeah. So yeah, I'm remembering over the top of my head. So when you give a sinusoidal input of 0.1 hertz, the output pressure, if you plot the FFT also, it will be close to 0.1. Similarly, you plot the input and the output dominant frequency, both should match for all experiments. That will demonstrate that you can approximate the system as an LTI system, point number one.
Yeah.
Okay. Then what you do is that for each experimental data, you take the steady state pressure, divide the magnitude by the steady state, input magnitude, and then you will be getting the amplitude, right, or the magnitude which you plot in the Bode plot. Of course, you need to take log 10 and then multiply by 20, right? So if you go from 0.1 hertz to 1.2 hertz, how many frequencies did we give? Was it in increments of 0.05?
0.1, 0.2, 0.3, like that.
Let's say there were like 14 data points for the sake of this one, right? So you will get 14 magnitudes. This is frequency. You plot the Bode plot, you will get a shape, right? Okay. And from the step response data also, you figure out which, what kind of response it looks like. Like whether it looks like more like a, first order function, first order response, and so on, right? And from the step response, you will be able to also like figure out, what is the gain, K, right? And also the time constant, right? And you can double check it from the frequency response characteristic also. How can you double check from the frequency response characteristic? Because when you plot the frequency response Bode plot, it will look like a first order function, right? And for a first order factor 1 by Ts plus 1, what is the corner frequency? 1 by capital.
1 by T.
1 by T, right? So from the experimental data, you will be able to get approximately the corner frequency, and that is 1 by T. So you can double check even with the step response whether the T that you get from the corner frequency data matches broadly with the step response data. Okay, so you need to smartly use both data sets to figure out the transformation.
Okay. Got it. So just a follow-up question on that. Am I audible?
Yes, please go ahead.
Yeah, so we will be using a semi-log X function in MATLAB actually, and in that we are giving two arguments majorly. One is the frequency in radian per second, and your magnitude in decibels, right? So
What is semi-log X function in MATLAB?
The semi-log X function in MATLAB, my understanding is
semi-log X function. Okay,
semi-log X, yeah. So my understanding is this is what we are using to plot the Bode plot. Am I right?
See, I leave the coding part to you, Prem. Okay, so yeah, right. So I think it's fair to all of you that you figure out your own mechanism to code. I will teach the concept. The code part I will leave it to you. You can ask questions to Abhinav, okay, by projecting the code when you meet him next Tuesday. All right. Okay. I hope that's fine, Prem. Because the MATLAB function and all, I don't want to comment without seeing the entire code, Prem. Okay, so you can show it to Abhinav, and then he should be able to clarify specific queries on the MATLAB function. But I hope I have clarified the concept, right? How you will use both the devices, right?
Okay, sir. Okay, got it. Yeah.
And is the project also sort of like unclear and fuzzy?
Little bit, sir.
Yeah, then the purpose is achieved, right? Like homework problems, if everything is clear and obvious, then I'm not doing my job, right?
All are like that.
So, but I think that's how we learn, right? So practical problems are going to be like this. Right? So we will learn together. Okay. So there is no unique answer here. Okay? So once again, we also want to figure out how each one of you thinks, but there is a unique process. So I hope we can do that, right? Any other questions?
Sir, one question I was having in the mind, but it is off topic, sir, and I was not able to gather the courage to ask you. But if you allow, can I ask this question?
Please go ahead.
It's basically while telling the story of what I mean to say, the disc brake and drum brake. Why drum brake was not able to get commercialized, although it was invented very early.
Yeah, disc brake.
Disc brake, sorry, sir. So basically, used a statement that you should be at right time, right position, at right time, doing right things. That's the life goes like,
Correct,
right, sir?
correct. Yeah.
So what is the deeper meaning of this sentence, sir? I just want to understand your perspective of that.
So see, many times, Roshan, we essentially, like in life, yeah, all of us put in effort, but we also need that chance or element of luck, right? To scale things up or achieve quote unquote success, right? So I think that is the intention, right? So essentially, you see, if let's say we lived 120 years ago, right? And still people were inventing electric vehicles and so on, right? But they could never commercialize it, correct? I'm once again sticking to automotive examples. But let's say today you do electric vehicle design, you have an opportunity, right? Because there's a market, there's an environment for it, right? You take it from that perspective. Okay? So same story I can give you here also, right? See, state space is nothing new, right? So people have been looking at it for centuries, right? So it's just that through my own research, I could figure out some automotive flavored up way of conveying transfer function and state space. So I'm getting the opportunity to share that with industry professionals like you, right? So in a certain sense, there is an element of luck playing in my case also, right? So I have given an example even from this own interaction. And see, what would give us most joy is that from this program, if you apply some of these ideas to your own practical problems that you face in your company, then you are able to make a difference or solution. That's once again, learning the correct thing at the correct time. Is it not, Roshan?
Of course, sir. Of course.
Okay.
So thank you for your explanation, sir.
Okay, thanks for all your questions, Roshan, Prem, and Keshav, and team. All right, please keep asking questions. I will try to answer to the best of my ability. But I think the message that your batch has also given me is that I should make the final exam more challenging, right? Because all of you are putting a lot of effort, right? And I think I should also challenge you.
The efforts are towards learning, not to challenge ourselves.
Only for learning.
Only for learning, is it? Okay. So yeah, I think Arunachal, is everyone present here today?
Yes, sir. Sorry, all are present, sir.
I'll mark attendance as everyone. So we will continue next Monday then, okay? And then we will continue from there, right? Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
And please do try out the project. If you have questions on the code, that is the programs, right? That's what I clarified even when we met in person. You please share the screen with Abhinav and ask him questions. Okay, so concepts we can discuss. Okay, yeah.
Okay, sir.
All right. Okay. See, yes, you can use MATLAB, you can use C program, you can use whichever Python or Scilab, whichever software you feel like to solve the. If you use MATLAB, the advantage is that many of the commands like what Prem told are already built in, so you don't need to program from scratch. Okay.
Got it, sir. Thank you so much.
Thank you, sir.
Okay. All right.